A point traverses along x-axis with a velocity whose projection vx is presented as function of time by the plot in figure 1.3. Assuming the coordinate of the point x equals 0 at the moment t equals 0, draw the approximate time dependence plots for the acceleration wx, the x coordinate, and the distance covered s. In this question, the point is traveling in x direction and its velocity vx time dependence is given in this plot. So we can see the velocity of the point at different interval of time, and we can write these intervals here. So the interval 0 to 1, the velocity vx is t. We can see this by writing the equation of this straight line. And in the time interval 1 to 3, the velocity is 1. In time interval 3 to 6, the equation of velocity can be obtained by the equation of straight line from the time interval t equals 3 to t equals 6. So this will be vx plus 2 equals minus 1 times t minus 6. And in the time interval t equals 6 to t equals 7, the time dependence of vx can be written in equation form by writing the equation of a straight line from 6 to 7. So the equation of straight line will be vx minus 0 equals 2 times t minus 7. And after time t equals 7, we can see that vx is constant and its value is 0. So we write vx equals 0 at t greater than equal to 7. Now what we need to do is we need to write the time dependence of the variables wx, x, and s in the time intervals given in the figure. So we first write the vx in the time intervals, and we then obtain the value of wx in the time interval by the formula wx equals dvx by dt. So in the first interval from 0 to 1, vx is t, so wx will be dx by dt of t, which will be equal to 1. And in the interval 1 to 3, vx is constant, its value is 1, so the acceleration will be 0. And interval 3 to 6, vx is minus t plus 4, so its differentiation with respect to time will be minus 1. In the interval 6 to 7, vx is 2t minus 14, so its differentiation will give wx equals 2. In the interval t greater than 7, vx is 0, so acceleration also will be 0. Now our next task is to obtain the displacement in x direction in these time intervals. So for obtaining the displacement, we use the formula x equals integral of v dt with the limits as given in the different intervals. For first interval, we will give the time limit 0 to 1 and we'll obtain integral dx equals integral v dt. So if you put the limit x minus 0 equals t square divided by 2 with the limit 0 to 1, and we'll get 0.5. In the next interval, velocity is constant, so the value of x will be x minus 2.5 will be the integral of constant, so it will be t. If you put the lower and upper limit, we will get the lower limit 1 and upper limit 3, so the value will be x equals 2.5. So similarly, in the next interval, we will integrate the value minus t plus 4 and we'll get the integral as minus 0.5 t square plus 4t. And if we put the limits from 3 to 6, we'll get the value of x as x equals 1. In the interval of time 6 to 7, we need to integrate the function 2t minus 14. On integration, we'll get the function as t square minus 14t. and if we put the limit from 6 to 7, we will get x minus 1 equals minus 49 plus 48, which will be equal to minus 1, and the value of x will be 0. For the time t greater than 7, Vx is 0. So the value of x will not change since the point has stopped moving. Now our next task is to calculate the distance in these time intervals, distance covered in these time intervals. So for distance covered, we need to take the modulus. In the first time interval, velocity is positive, so distance will be equal to displacement. In the second time interval from 1 to 3, velocity is positive, so distance will be equal to displacement. And in the third time interval from 3 to 4, the velocity is minus 3t plus 4, so the value of velocity is positive, so distance will be equal to displacement. And till this time interval, the distance and displacement will be equal. And after that, we can observe that from t equals 4 to 6, the velocity is becoming negative, and in this time interval we need to take the modulus of displacement. So we obtain the displacement by integrating the function for velocity, and we take the modulus to obtain the distance. So we take the modulus of this integral value minus 0.5 t square plus 4t from 4 to t. To plot the function, we need to integrate from 4 to t, and we can put the lower and upper limit to get the distance at t equals 6, s equals 5. Similarly, for the next interval, we will integrate to obtain the displacement, and we will take the modulus to obtain the distance. And in this interval, we get the distance at t equals 7 equals s equals 6. And for the time interval greater than 7, the velocity becomes 0, so point is not moving, so distance will remain as it is and it will not change. Now the next step is to plot these functions which is asked in the questions. So first we will plot the acceleration which is given here. We can see that acceleration has constant values in different time intervals. So considering these values, we can plot the acceleration. Here it is shown with the green line. From the value of time 0 to 1, the acceleration is 1 constant value, so the plot will be parallel to x-axis. From 1 to 3, the constant value is 0, so again the plot will be parallel to x-axis and it coincides with x-axis. And from 3 to 6, the plot is parallel to x-axis, the acceleration value is constant and its value is minus 1. So for the time interval 6 to 7, the acceleration value is 2, so the plot will be parallel to x-axis and it is shown with the green line. Similarly, we can plot for the displacement, which is shown by the black line, dark line, and dark dotted line shows the distance. So the value of displacement is shown for the different interval, and the function value is shown the integral with respect to time. So this function of time should be taken care while plotting to get the more approximately equal curve. And we can plot the displacement and distance we have plotted by the dotted line till the time equals 4. Since velocity is positive, the displacement and distance are equal, and after that velocity is negative, so displacement is decreasing while the distance is an always increasing function, so it cannot decrease. So this is how we plot the acceleration, displacement and distance with respect to time.